Earth, a 4.5 billion-year-old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede, the Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, Iceland, the world's largest volcanic island, is explored. This barren and alien landscape generates 1/3 of the world's lava. Steam billows from the ground, and boiling water is thrust into the air. It's a land of violent extremes where fire meets its nemesis, ice. And where clues to understanding Iceland's formation also provide a window into the formation of the Earth itself. In the middle of the North Atlantic Ocean lies Iceland, a lone island, only 300 miles wide. A volcanic hotbed, it holds some of the most diverse geological wonders known to mankind. To understand how it formed and the dynamic forces that are shaping this land, scientists are scouring the strange landscape for clues. And the investigation starts here in the southwest of Iceland, the Thingvellir Plain. This broad inland valley runs through the center of Iceland. Giant cracks scar the valley floor, leaving this unusual landscape behind. Geologist Mike Poland believes they're a major clue in the mystery of Iceland's formation.
I'm standing in a really spectacular place. There's evidence for volcanic activity all around. This valley is covered in lava, and the plain is being ripped apart. Everywhere I look, there's massive tears in the ground, like this one right here. This crack is getting bigger and bigger every year. In fact, this entire valley is spreading apart at about the same rate that fingernails grow. Now imagine the forces that must be involved to rip the land apart like this.
Something powerful is spreading this valley at a rate of 1 inch a year. A force so immense, it's pulling the entire country apart. But what force on Earth could have such power? In 1912, German climatologist Alfred Wegener found an essential clue. Browsing through maps, he noticed that the great land masses of the Americas and Eurasia appeared to fit together. This observation led Wegener to propose a radical new theory: that these great continents had once been joined together. So some unseen force must have pushed them apart, allowing water to rush into the space between them, creating the Atlantic Ocean. It was inspired detective work and a major step forward in the search for what was pulling Iceland apart. But with no method to prove such a force existed, Wegener's theory was ignored for the next 40 years. Then, in 1946, new evidence was discovered to support Wegener's ideas. The U.S. Navy, using a technology called sonar imaging, mapped the Atlantic Ocean floor for the first time. The pictures revealed a 10,000-mile network of underwater mountains, separated by a giant tear which passes through the center of the Atlantic. Scientists call this the Mid-Atlantic Ridge. This huge tear through the Earth's crust is the boundary between the American and Eurasian plates. And the tear runs right through the center of Iceland.
I'm actually standing on what's essentially the ocean floor, where the Mid-Atlantic Ridge comes onto land. And it splits the North American plate on this side from the Eurasian plate at this side. And the Mid-Atlantic Ridge starts way south, down by Antarctica, comes all the way up through the Atlantic, and splits this country right in two.
Scientists suspected this was pushing the continents and Iceland apart. They came up with a theory. Deep below the ocean, convection currents of molten rock tear open the Earth's crust, allowing magma to seep up and push the continents apart. But there was a problem. It was so deep, scientists had no way of proving whether magma was seeping through the crust at the center of the ridge. Until in 1974, Alvin, a human-operated submersible, was launched by the Woods Hole Oceanographic Institute. With its ability to withstand deep-sea pressures, scientists could finally travel down to the depths needed to reach the mid-Atlantic ridge. It was by examining the tear that runs through the center of this ridge that they spotted the evidence they'd been looking for. Hot volcanic gases billowing into the ocean. Finding this told them that the mid-Atlantic ridge was highly volcanic and, like a giant wedge, was capable of spreading great land masses apart. Iceland's cracked Thingvellir Valley is a continuation of the mid-Atlantic ridge. The same process that's pushing America further away from Europe is happening here on land. Finally, here was a force powerful enough to explain why the cracks are getting wider and Iceland is getting bigger. The investigation into how Iceland is growing has revealed cracks on the Thingvellir Plain are widening at a rate of 1 inch a year. And hot gases prove that this spreading force is volcanic, forming the mid-Atlantic ridge, which cuts right through Iceland. Scientists concluded it's this that's widening the country. Convection currents of hot rock pull the mid-Atlantic ridge apart. Magma surges up to fill the cracks, and as it approaches the surface, it cools, hardens, and forms new land. Like a conveyor belt, it continually pushes Iceland apart. But something didn't add up. Why wasn't Iceland at the bottom of the ocean like the rest of the mid-Atlantic ridge? There's something strange about the amount of volcanic activity on this island. The hunt is now on to discover how Iceland rose 1.5 miles off the ocean floor and became the biggest volcanic island in the world. Iceland. There are more active volcanoes concentrated here than anywhere else on the planet. Geologists are searching for what has helped push Iceland off the ocean floor and lights the fiery volcanoes that rage across this barren land. On the hunt for clues, the investigation heads to one of Iceland's most active volcanoes, Hekla, known locally as the Gateway to Hell. Like all active volcanoes in Iceland, Hekla sits alongside the mid-Atlantic ridge. Volcanologist Dr. Pete Lafamina is taking a high-resolution scan of the volcano to see if its geology hides any clues about its inner workings.
This is a terrestrial laser scanner, and the laser produces a 3D image of the Earth's surface, and that allows us to see parts of Hekla volcano here that we can't see with the naked eye.
His scan reveals a giant crack or fissure running right through the center of the volcano, similar to those found in the Thingvellir Valley. But this fissure doesn't just span the width of the volcano. It extends either side along a 5-mile tear in the Earth. It's this tear that's key to understanding how Iceland's volcanoes erupt. When Hekla erupted in the year 2000, it wasn't just the volcanic cone that exploded. The Earth actually ripped open along the entire 5-mile length of the fissure, a weakness created by the stretching along the mid-Atlantic ridge. In the geological world, these are known as fissure eruptions. Forced open by the sheer volume of magma pushing up from below, the tear spewed out a terrifying 750 million cubic feet of molten rock an hour, flooding the land with lava. These fissure eruptions are so huge, they can change the landscape drastically in a matter of days, leaving behind mountains like these.
You can see to the north here where the Earth's surface actually opened up during a fissure eruption and lava erupted out. This fissure starts to the north and extends 8 kilometers through Hekla volcano here. The sheer volume of magma produced can be seen very well here at Hekla volcano, especially with these lava flows that have draped the land surface. And to me, this is really exciting because you can see very large volumes of erupted material produced over very short amounts of time. And Hekla is a beautiful place to study that.
But what is creating the vast quantities of lava that are forced out during these eruptions? For many years, the answer remained elusive until geologists found incriminating evidence locked inside the rocks.
The composition of the rocks here in Iceland is quite different than we see in other places. By taking this rock back to the lab, we can get a very good idea of under what conditions it formed, whether it formed deep within the earth or near the surface.
This rock was once molten lava, which erupted from one of Iceland's volcanoes. Analysis of the chemicals in the rock revealed unusually high concentrations of rare earth elements lanthanum and cesium, chemicals which are only found in magma with a very deep origin. It's the breakthrough scientists had been searching for. It was evidence that another, much deeper heat source was combining with the mid-Atlantic ridge to power the volcanoes of Iceland. The rock evidence suggested this second force lay hidden from view, deep beneath Iceland's surface. But it is possible to get a glimpse of what's happening down there. Scientists monitor the seismic waves triggered by earthquakes all over the world. As the Earth's plates move, they release shock waves, called seismic waves, that pass through the Earth's crust. These travel at a steady speed unless they hit a region of hot rock. Then they slow down.
Now, as seismic waves arrive in Iceland, they're traveling very slowly through the subsurface. And this is somewhat unique to Iceland and a few other places in the world. It tells us that there's a very hot column of rock, perhaps even some molten material beneath the surface.
These massive columns, or plumes, are known as hotspots and are not unique to Iceland. They are found beneath certain volcanic areas in the world, like Hawaii and Yellowstone.
Hotspots are these unwavering plumes of hot material, including molten rock, magma, that stream up to the surface from deep within the Earth.
The scientists finally had a snapshot of the second force that was helping to create Iceland. The hotspot that lies beneath the island is almost 100 miles wide and 400 miles deep. It channels rock slowly upwards at temperatures over 1,700 degrees Fahrenheit. It pushes against the crust, heating the land from below and forcing magma up onto the surface as lava. The investigation has identified the two colossal forces that built Iceland: the mid-Atlantic ridge and the deeper Icelandic hotspot. Millions of years ago, the mid-Atlantic ridge drifted eastwards, creeping towards the fixed Icelandic hotspot. Finally, they met and have been locked together in a deadly partnership ever since. The result? A truly formidable volcanic beast, capable of creating magma on a monumental scale.
As the mid-ocean ridge pulls apart, There's decompression of the material underneath it, and that creates melting. Decompression is simply removing the pressure from a pile of rock. It's much like opening a can of soda or popping the cork off of a champagne bottle.
The removal of so much pressure makes the rock melt into liquid magma.
Now, the hotspot is transporting heat directly from the interior of the Earth to the surface, which also creates melting. So this combination of decompression of existing rock beneath the surface and the direct transport of heat from the center of the Earth create a huge amount of magma.
This incredible meeting of the mid-Atlantic ridge and hotspot began to build the island beneath the waves, pushing it upwards and giving birth to Iceland. Scientists have dated the island's emergence to 20 million years ago, but could only imagine what this might have looked like. But on November 14th, 1963, off the south coast of Iceland, the world watched an action replay of Iceland's spectacular birth. A column of rock and ash blasted out of the ocean 18,000 feet into the sky, so high it could be seen 70 miles away in Iceland's capital city, Reykjavik. A new island was forming right in front of the world's eyes. Scientists called it Surtsey, after the Norse god of fire, Surtur. Located 20 miles off the mainland, the small island of Surtsey is now a magnet for geologists. It offers a wealth of forensic evidence for Dr. Lafamina, who is investigating how Iceland first formed.
This type of eruption that forms Surtsey has now been named after Surtsey. We call them Surtsean eruptions, and they're very, very explosive. The interaction of hot magma or lava with the ocean causes these very steam-rich and highly explosive eruptions of ash and water.
When scientists first stepped foot on the island in the summer of '64, they found it hard to believe that this was an island whose age was measured in months, not millennia.
In about 9.5 months, this whole volcanic cone built up. In addition, lava flows came out of the volcanic center here, and we're seeing these nice black cliffs in front of us.
Now geologists had an insight into how early Iceland might have formed. In only 20 million years, Iceland grew from a tiny island into a 40,000 square mile landmass, as big as the state of Kentucky. The forces that power Iceland's volcanoes have been revealed. Cracks along Hekla volcano unleash gigantic fissure eruptions, and rare chemicals in the rock prove that these eruptions were fueled by two separate forces, the mid-Atlantic ridge and the hotspot. Iceland grew to become the world's largest volcanic island. But volcanism alone doesn't explain how the land of Iceland was formed. The investigation will unearth another equally dramatic force that sculpted the distinctive shape of the Iceland we know today. A force which would challenge the might of Iceland's volcanoes. If Iceland was formed by fire alone, it should look like other volcanic islands such as Hawaii or Tahiti. But something else was at work here to transform this island into the distinctive shape it is today. Its shape is another clue to Iceland's formation. An extraordinary force indented Iceland's northern coastline, burrowing deep fjords which extended far inland. But what colossal force could cause such a dramatic change to Iceland's volcanic landscape? There's an obvious suspect that's found scattered across the island: ice. As its name suggests, Iceland has a long history of being covered in ice like this. Today, it covers 10% of the island, all year round. And in the middle of the country lies Europe's biggest ice cap, the mighty Vatnajökull. Over 3,000 square miles in size, Vatnajökull is so large it even has its own climatic conditions. Up to 2/3 of a mile thick, it squashes the land like a giant slab of rock, and at its edges, great tongues of ice flow out through deep valleys. Glacier expert Dr. Matthew Roberts is investigating how ice can gouge out solid rock and discover the role it has played in Iceland's past.
This is a GPS receiver, just like in-car satellite navigation. It's used here to measure glacier movement. This will be left on the ice surface for a few days, and then I'll come back and analyse the data and discover just how far the glacier has moved.
Dr. Roberts' data reveals that this whole glacier is sliding forward at an astounding rate of 2 feet per day.
This is an amazing, ever-changing environment. The ice around me is like an icy sea that's been frozen in place. As the ice flows out of the confines of the valley, it expands and spreads to occupy a greater area. Now, as it expands, crevasses form and large depressions, just like the one here. Here's a smaller crevasse that's formed. Occasionally, when these crevasses open, as they begin to open, sounds can be heard. Also, the glacier occasionally makes a groaning sound. This is all signs that the glacier is alive and moving forward very slowly.
Vatnajökull is one of the largest ice caps in the northern hemisphere. Flowing down the valleys, the great mass of ice bears down with the weight of 100 tons per square foot. Dr. Roberts believes this moving giant is a force capable of eroding solid rock, and he's found crucial evidence to prove it.
This is an excellent example of the power of glacial erosion. This boulder would have been trapped beneath the base of the ice, and as the ice flowed over the surface of it, it would have progressively eroded the surface of the boulder to produce these very distinctive marks called striations in its surface. We can even tell the direction in which the ice was flowing. If I take a rock, I can illustrate this. Imagine this is the base of the ice, material trapped inside the ice, being dragged across as the glacier moved to produce these very distinctive marks in the surface. This is just like sandpaper over wood, the same erosive effect.
The erosive process that's happening on this boulder is the same process that's happening on a much larger scale along the surface of these valleys.
The glacier is responsible for literally carving the landscape, producing very distinctive troughs and basins which were formerly infilled with solid rock. This really testifies to the erosive power of a glacier.
The ancient fjords on the north coast are the same deep basin shape, which means they must once have been filled with ice. Scientists now know that around 1.5 million years ago, changes in the Earth's orbit and the tilt of its axis began to cool the planet. An enormous ice sheet descended from the north and shrouded Iceland in a cloak of ice. As the ice advanced and retreated, it carved out deep fjords and indented Iceland's northern coastline. Ice was a formidable force in Iceland, and many volcanoes lay entombed beneath it. Fire and ice were now locked in a titanic battle of supremacy. Would the giant ice sheets that carved the fjords put out the fires that created Iceland? The first clue lies in this ancient valley, 5 miles west of the glacier. The valley floor is strewn with hundreds of giant boulders, but it's how they got here that interests Dr. Roberts.
These boulders provide a lot of insight into how this landscape was formed. The boulders are clustered together, and interestingly, these boulders are rounded, which shows that they've been rolling. Now, the boulders have been brought together by some dynamical force. We can also see smaller boulders trapped in the centre, and it's quite clear that flowing water is the cause of this. But this wouldn't have been water in the stream that we see in the background. This would have been water produced by a much larger, faster flow that would have inundated this entire valley.
Dr. Roberts has an extraordinary theory about what happened here. In ancient times, a cataclysmic flood 100 feet high cut through this valley. It was so powerful that it rolled these giant boulders like pebbles in a stream before dumping them on the landscape. But what could create such a colossal flow of water? Dr. Roberts suspects the flood came from the mighty Vatnajökull Glacier and is hunting for clues. With such a huge area to cover, Dr. Roberts takes to the air. His investigation leads him to a crucial piece of evidence. This strange bowl-like depression on the surface of the ice.
This is an amazing location. This giant depression in the ice has been formed as a pocket of water is drained from beneath the base of the ice cap. The beautiful concentric crevasses that you see on the ice surface have formed as the ice has slowly crept into the hollow that's been created as the water is drained away.
Beneath the ice, a dynamic process is happening. Hot magma and steam are melting the glacier from underneath. The meltwater collects in a huge ice basin at the top of the volcano. The basin slowly fills, but as it does, the surrounding ice becomes unstable. Cracks appear in the ice basin, and as the hot water drains away, it forms a tunnel which channels the water to the edge of the glacier. This would suggest that volcanic eruptions still happen, even under the enormous weight of ice. Is this process the key to explaining the ancient cataclysmic flood? To answer this, we must go to one of Iceland's largest volcanoes, Grímsvötn. Lying entombed beneath the ice in the heart of Vatnajökull, this massive volcano violently erupts every 10 years. Here, fire and ice spectacularly collide, with Iceland's volcanoes emerging victorious. Ice cannot suppress the invincible power of Iceland's volcanoes, which have now found a new way to vent their anger. During a huge eruption like this, Grímsvötn can melt enough ice to fill America's largest man-made reservoir, Lake Mead. But this vast volume of water cannot be held back by the ice for long and leads inevitably to a massive glacial flood. Such a force of nature struck Iceland in 1996 with devastating consequences. The floodwater taking out everything in its path. Bridges were torn down and swept away, and the highway was submerged underwater.
The flood itself reached a peak discharge of over 1.8 million cubic feet per second. That's a remarkable discharge, equivalent to the summertime discharge of the river Amazon. Imagine that sort of condition over a relatively small area.
The sheer force of the water carried icebergs the size of 4-story buildings. It's floods like these that can change the landscape in a matter of days.
The erosive power of the flowing water can result in tremendous amounts of rock being eroded, literally being fractured away by the high water pressure that's being created. So literally a landscape can form before your eyes during a very severe glacial flood.
The story of Iceland's bizarre landscape is taking shape. Striations on rock prove that ice is a formidable force that carved out Iceland's unique coastline. Boulders strewn in an empty valley reveal cataclysmic floods of the past. And depressions in the ice confirm that Iceland's volcanoes could not be suppressed. But 12,000 years ago, the great ice sheets retreated, and Iceland was liberated from their wintry grip. Now, the effects of Iceland's volcanoes would be felt on a global scale. For thousands of years, Iceland's volcanoes were locked in a titanic battle with ice. But then 12,000 years ago, the giant ice sheets finally retreated. This would open a new chapter in Iceland's volcanic history, as they were now free to wreak havoc. But what effect would this have on Iceland and its surroundings? One of the most dramatic effects can be found in the south-central region of the island. This alien landscape is known as Larky, a row of strange craters and solidified lava flows that have bubbled up from a huge tear in the earth. A massive fissure eruption, it stretches for an astounding 16 miles across the landscape. Volcanologist Dr. Thor Thordarson is investigating Larky, the site of one of the greatest eruptions in recent history, one which would have devastating effects worldwide.
The Larky fissures, which extend from here in the southwest, continue here through the landscape as a row of cones up here through Mount Larky, which was split into two during the eruption, and continue further to the northeast all the way to the margins of the glaciers here.
Eyewitness accounts accurately date the eruption to 1783. This was one of the most disastrous years in Icelandic history. Fallout from the eruption caused harvests all over the island to fail. 75% of the livestock died, plunging Iceland into a great famine, which killed 10,000 people. But mysteriously, at the same time, the rest of the northern hemisphere reported freakishly cold weather. Averaging 2.3 degrees Fahrenheit below normal, the northern hemisphere froze over.
The North Sea along the coast of Holland froze, so people skated between villages along the coast. There was ice on Mississippi down by New Orleans in that winter.
For many years, it was thought the Larky eruption and these climatic events were unrelated. But advances in geology found it wasn't just a bizarre coincidence. Comparing eyewitness accounts with the geological remains, Dr. Thordarson has reconstructed what happened. He discovered that the eruption started with a bang on the morning of June 8, 1783. It sent rocks flying high into the air and ripped the earth open along a 1-mile tear. But this was just the beginning. 3 days later, a second eruption ripped open, then a third, fourth, fifth. In total, the earth unzipped along 10 vast tears in the crust, erupting lava continuously for over 8 months. The mammoth amounts of lava that poured out of the ground here would have buried Manhattan to a depth of 830 feet. But how an eruption on this small remote island could cause climatic chaos thousands of miles away remained a mystery. The evidence that would link Larky with this worldwide catastrophe was locked inside these boulders.
The story is in the rocks. This rock here is part of the material, the magma that came out during the eruption. These holes are called bubbles, and they form as the magma rises from deeper in the ground and approaches the surface, and it really starts to boil. The gas, which is dissolved in the magma at depth, goes into the bubbles. Then it escapes into the atmosphere.
When this bubble rock erupted onto the surface, it would have poured gas out into the Icelandic atmosphere. Could this gas have caused climatic chaos across the globe? The identity of this gas can be found in the microscopic structure of the rock.
If you look closely at this rock, you can see a lot of white specks. These little white specks are crystals who grow in the magma at depth. Sometimes these crystals, as they're growing, they will encapsulate pristine magma and bring it up to the surface.
Like time capsules, the white crystals contain untouched magma from deep in the earth, locked away since 1783. Dr. Thordarson has analyzed this magma and found it to contain poisonous sulfur dioxide. And because there was so much lava here, it would have released enormous amounts. A staggering 100 million tons of sulfur dioxide gas was pumped into the atmosphere. But how could gases released from Larky cause bitterly cold weather across the globe? The answer lay in accounts of a thick red fog reported over Iceland in June 1783. Within a few weeks, it had been blown over London and Paris, and by July, it had dispersed across the entire northern hemisphere. Scientists now know that the red fog was caused by the sulfur dioxide which rose high into the air. Mixing with water, it created a sulfuric acid haze. The haze blocked out the sun, and it sent temperatures plummeting. As a result, the northern hemisphere endured 3 bitterly cold winters, which brought spring floods, famine, and widespread poverty to Europe. Some historians have long believed that these climatic conditions triggered social and political unrest, which led to the French Revolution in 1789. But scientists now suspect Larky had ramifications even further afield. The cold temperatures in the north changed air currents in the south, causing dramatic climate changes. India was hit by a terrible drought.
People say that more than 500,000 people died from the drought in India. Also, this change in atmospheric circulation caused a very cold summer in Japan. It's cold and wet. The rice harvest failed, and the result was the greatest famine in Japanese history.
It is estimated that Larky killed over 2 million people worldwide and was one of the most devastating volcanic eruptions in the history of mankind. The evidence has proven that Iceland's recent volcanic history has had a devastating effect on the island and the rest of the world. Enormous lava fields reveal that Larky was a gigantic eruption. Bubbles in the rock indicate that huge volumes of gas were released from Larky. The white crystals reveal that this gas was poisonous sulfur dioxide. Evidence that Iceland's volcanoes caused climatic mayhem across the globe. But eruptions like Larky may not be confined to the past. Some believe that the balance between fire and ice is shifting and has the potential to propel Iceland into another hell on Earth. The evidence is mounting that Iceland has the potential to be the most lethal island on the planet. A fearsome volcanic force lies beneath it, creating powerful volcanoes capable of generating gigantic lava flows and altering global climates. Yet many of Iceland's volcanoes are covered in glaciers. Fire and ice are held in a delicate balance. Scientists fear if this balance were tipped in the volcano's favor, Iceland could become even deadlier. If the remaining ice were to melt, what effect would it have on the activity of Iceland's volcanoes? The first clue in the investigation lies in these innocuous-looking piles of rock and rubble. They're found all over Iceland, and yet these rocks don't come from a volcano. They're moraines, the geological term for rock piles deposited at the mouth of a glacier. These deposits are evidence that the glaciers are shrinking. Year by year, the glacier has melted and retreated back up the valley, leaving a moraine like this behind. Dr. Roberts has studied the Vatnajökull Glacier for the last 10 years. and has noticed this dramatic trend.
The glacier has retreated at a remarkable rate. Since I've been visiting the area, I've seen tremendous changes. The ice has retreated annually at a rate of about 200 feet per year. This lake over here used to be filled with ice. I've seen the ice progressively melt, this moraine has formed, this whole valley has become almost bare. Maybe in the next 20 years, this whole glacier will disappear and a lake will form in the valley.
Iceland's glaciers are melting at an unprecedented rate. With 5% of Iceland's ice caps melting in the last 40 years, the question that scientists are keen to understand is what effect this rapid melting will have on the volcanoes that lie beneath. The only other time that glaciers have melted this quickly is when Iceland came out of the last ice age. But what can past events tell us about the future? Geologist Professor Bill McGuire is investigating how volcanic activity changed at the end of the last ice age, and he's unearthed some surprising results.
Around about 11 or 12,000 years ago, you started to see quite rapid melting of glaciers in Iceland and elsewhere, and that triggered a recognizable increase in volcanic activity because you were removing this large mass of ice very, very quickly.
The rapid melting of ice kickstarts volcanic eruptions beneath.
Volcanic eruptions are triggered by the gas in the magma, which expands to form bubbles, and the bubbles drive the eruption. It's rather like taking the cork out of a bottle of champagne. Now, if you have a very heavy weight on top of a volcano, if there's a heavy mass of water or ice, that can help suppress eruptive activity.
But when ice melts quickly, this downward pressure is suddenly released. And that's when the trouble starts.
As the ice melts, so the pressure on the magma underneath is reduced, the gas in the magma can form bubbles, they can coalesce, and they can eventually drive the magma upwards towards the surface and trigger either explosive eruptions or effusions of lava that can spread out over huge distances.
Iceland's glaciers are melting rapidly. This has led scientists to believe that a devastating eruption on the scale of Larky could happen again.
The question is when. These are things that we have to think about and try to prepare ourselves to deal with if they happen in our lifetime. Is it possible that we can get another eruption like this in Iceland? Definitely.
The investigation has revealed how the vast and violent island of Iceland was formed. Cracks in the Thingvellir Plain and traces of chemicals in the rocks revealed how the Mid-Atlantic Ridge and hotspot joined forces to create a colossal volcanic force. Massive fissure eruptions ripped the land open. Hemorrhaging millions of tons of lava, Iceland rapidly formed. Deep northern fjords were evidence that a giant ice sheet eroded the land and entombed the volcanoes, locking fire and ice in a titanic battle. Boulders strewn in an ancient valley revealed how fire emerged victorious, unleashing cataclysmic floods. And specks of sulfur in the rocks showed how Iceland's volcanoes have the potential to cause global destruction. Now, glaciers melting above some of the world's most deadly volcanoes are increasing the threat of future eruptions. Over the last 20 million years, Iceland's almighty volcanic force has created a vast alien landscape. Volatile and unpredictable, it may one day unleash a massive eruption which could devastate both Iceland and the wider world beyond.